do it up. Let's look at this. So I want to start with the evaluating because evaluating is easy and it will sort of lead us into the graphing. So when I say evaluating, what I mean is putting a number into your function, right? That's or something else. You can put other things aside for numbers, but we're going to start with numbers. So let's say I have a very simple function. F of x equals, let's say 1 minus 3x. Something easy. If I want to do f of 2, whatever I put in the parentheses, that's what goes into the in for the variable. So I noticed that I put my 2 in for x here, right? So got this and this. So 2 is replacing the x, and so it replaces the x in the function, or when you're plugging it in, I guess. I don't know what to call that in the formula, I guess is what I'm trying to say here. So that's -5. That's it. There's really not much else to evaluating functions. I want to remind you of the problems that you can have with domain, where if you try and put in something that gives you a nonsense answer, or not nonsense, but an answer that we can't use, a non-real answer, like you're trying to take the negative or take the square root of a negative number, or if you are trying to divide by 0, that leads to problems. We would just say that whatever input is not in the domain. So let's do something a little bit more complicated. We'll say g of x is, I don't know, some messy thing. X squared minus 5 divided by the square root of x minus 3 times. Let's see, what's another one we're using here? Let's say 2 over x. All right, so a couple things. One, this looks messy. That doesn't actually make it all that much harder, to be honest. And 2, we've got lots of stuff, lots of potential problems here, right? I've got a square root, so I got to watch out for things that'll make me take the negative of a square root, or take the square root of a negative number, excuse me. And I've got sort of 2 denominators here because I'm dividing by 2 over x, right? So I can't have x be 0, which would make it would make this bit 0, right? And I'd be trying to do 2 over 0. That's no good. I also can't let anything cause this to be 0, which it can't be, but that's a thing to watch out for. Yeah, so basically I'm just going to plug in something. What do I want to plug in here? So let me take a quick gander at this. So I want something bigger than 3, because anything 3 or smaller will cause this to not work. I don't want to use 0. So let's pick like 5. Right, so I'm going to pick something bigger than 5. So I'm going to find, oops, that's not what I meant to do. So I'm going to say g of 5 equals, excuse me, my Zoom is annoying me here. Well, 5 squared is 25. So I got 25 minus 5, absolute value, divided by square root of 5 minus 3 times 2 over 5. All right, and then we just simplify. So this is going to be, so 25 minus 5 is 20. I take the absolute value, it's still 20. So this is 20 over the square root of 2 times 2/5. Now, if you remember, so I'm currently dividing by 2/5. So I'm going to rewrite that as multiplying by 5/2. So this is 20 over, that's 20, not 26, root 2 times 5 over 2. And we cancel. We get a 10 there. And a 1 there. We get 50 over the square root of 2 equals 50 over root, excuse me. Pardon me, my computer didn't like what I've done there. I'm gonna grab all this stuff and just move it on up here where there's a little bit more room. So, pencil, 1 sec. So square root of 2. Right there. There we go. So you can see it's a little bit messier, but nothing you don't know how to do. You literally just put in the number into the formula and get out the function value. Now, the thing I want to remind you is that this thing in a box is g of x. That's my y. So it's pretty easy to get mixed up about what's x and what's y. The thing you come out with is y, right? So I would say, let me do another screen. So that was g of 5. Yeah, so we had g of 5 is 50 over the square root of 2. Right? So this guy right here is the x. This one is the y. Right? And so it's very easy to think to yourself that g of 5 is 5, right? I'll ask that question a lot and say, what's g of 5? People will just say whatever number they see on the problem. Let's say it's 5. It's not. The y value is g of 5. 5 is the x value. That's kind of all I want to say about evaluating functions. Now, I guess I got one more thing I want to say. You can put in things that aren't numbers too. So for instance, if I wanted to do g of, let's say, t, I would put t in for all the x's in this formula here. And you might say to yourself, well, that seems pretty straightforward. It's because it is. I'm literally just changing the name of the variable, right? The fact that it's a t doesn't really change much. T minus 3 times 2 over t, right? That's pretty easy. But that leads us to something a little bit bigger and more interesting, which we'll get into more when we get nearer to inverse functions, which is function composition. Because the things I can put in for x don't have to be just numbers or just a single letter. I can put in a function in there. So let's try a really simple example of that. Let's say I did g of, let's say, x minus 2. That is a thing I can do. So that's going to come out to be this. I'm just going to replace all the x's in the formula, or the t's in this case here, with x minus 2. So that's going to be x minus 2 quantity squared minus 5 over x minus 2 minus 3. And yeah, that simplifies, which we'll do in a second, times 2 over x minus 2. And now we can clean this up a little bit, right? So I can multiply the top out to give me absolute value of x squared minus 4x plus 4 minus 5. Right, so all I did was took this and multiplied it out to get that. And then in the bottom, x minus 2 minus 3 is just x minus 5. And then I can't really do much with the other thing, 2 over the x minus 2. And we can simplify this a little bit more, right? Plus 4 minus 5 is minus 1. So let me just do that on another page. We're going to x squared minus 4x minus 1. So x minus 2 was absolute value of x squared minus 4x minus 1 over the square root of x minus 5 times 2 over x minus 2. Right? So you see what I did there? I just put in x minus 2 instead of the t that I had there, and that was it. And that's really what evaluating functions is all about. It's just whatever's in here, whatever's in the parentheses here, goes in for all of your variables. And then you simplify. Sometimes that involves with numbers, sometimes that's with letters, sometimes it's a little bit of both. You can even do things a little bit more fancy here. I'm going to use my favorite example here, g of smiley face. Boop. So g of smiley face, if you remember, the top was absolute value of x squared minus 5. So I got smiley face squared minus 5. I like the parentheses. It makes it look like he has cheeks. Over the square root of smiley face minus 3 times 2 over smiley face. Boop. There we go. Now he looks like a little train conductor. He's got a hat. Yeah, that's it. That's really all there is to it. So sometimes it's a little grindy. Sometimes it takes a little bit of work to simplify it all, but that's what you do. You put a number in, there you go. The other thing I really want to talk about is there are there's kind of 6 graphs that are considered by a lot of math teachers to be sort of the fundamental graphs that most things are based on, and they are these functions. So functions. We've got x squared, x cubed, absolute value of x, what's the other one? Square root of x, and then 1 over x. So you can make most of the functions that you're interested in out of these guys. That's kind of true. There's a few others. There's logs and exponentials, as well as some periodic functions when you get to trig. But we'll just go with these. This is a good start for graphing functions. So you basically want to know what each of these things looks like, and really you just want to memorize it. I'll give you some tips. I'll show you how to remember what they look like, but remember them. Like that's important. I was going to do all these by hand, but I think it's probably just a lot easier to show you on Desmos, so I want to do that instead. Let's go look at Desmos. Where's my that one? Oh, I've got, oh no, that's not the right one. Hang on. Sorry. I apologize. I'm going to pause for a second. All right, there we go. Sorry, I had too many Desmos windows open. As you can see, I got a couple here and a couple more in other other tabs, or not tabs, but instances of Chrome. All right, so here we go. I got my 6 functions. So y equals x. You know what that looks like? It's a line with slope 1 and y-intercept 0, right? Because it's y equals 1x plus 0. So it's a line. Y equals x squared is a parabola. You probably knew that, but in case you didn't, this is what it looks like. If you want to, like, if you're not sure what this looks like, you can always just plot a few points. So if you want to know, if you're not sure what a graph looks like, so let's say you didn't know what x squared was, or you're mid-test and you've forgotten because you're nervous or whatever, what you can do is the following. Let's go back to the whiteboard for a second. And let's say I have my function of y equals x squared. And just flown out of my mind what that thing looks like. All right, do not panic. Here's the solution. Make a big table. Like, that's the way to do it. So I'm going to do x, y, and I'm going to use like 5 points is probably enough. -2, -1, 0, 1, 2. And then when I square x, so we have to evaluate this function a bunch of times, right? So I'm going to put -2 in for x and square it. So I do -2 minus -2 times -2 is +4, right? Because when I square a negative number, I'm doing negative times negative gives me positive. Similarly for these other ones, 1, 0, 1, 4, right? So then I just graph that. 1, 2, 3, 1, 2. That's not the prettiest graph I've ever made. 1, 2, 3. All right, so -2, 4, -1, 1, 0, 0, right there, 1, 1, 2, 4. And hopefully that reminds you what it looks like, right? So just whenever you forget what something looks like, plot a few points. Or if you have a calculator handy, just graph it on your calculator, so just so you remember what it looks like, right? That's just a nice, handy use of technology, to be honest. All right. This one? Yeah, that one. All right. X cubed looks like this. We'll talk about that one in just a second. Absolute value of x looks like y equals x, right? It looks like this guy, but only in 2 pieces, right? So for y equals x, it's got a slope of 1 and a y-intercept of 0. That's this line right here. And when x is positive, that is exactly the same thing that happens with absolute value of x, right? Same deal on the right side of 0. On the left side of 0, instead of being like -2, -2, it's -2, +2, or -4, +4, right? So on the right side, nothing, as long as x is bigger than 0, nothing happens to it. It just stays the same. On the other hand, on the left side, over here, when x is negative, the y value becomes positive, because the x is the thing that goes inside here, but the y value is what you get out. And absolute values take whatever you put in and make them positive, right? Whatever sign it had before, now it's plus sign. So when I put -2 in, I get +2 out. And when I put -4 in, I get +4 out. So this is another example of, if you forget what this looks like, just plot a couple points and you'll remember it. It should be pretty straightforward. This one is a little harder to remember, right? It's not necessarily obvious what that is. So let me show you what this is. So let me get a new whiteboard here. Come on. All right, so if I have y equals x squared, or y equals square root of x, right, which is that thing that I'm graphing, I want to square both sides of this, right? That's a thing I can do because this is an equation. So I end up with y squared equals x when I do that, because squared and square root cancel each other out. So let's go see what that looks like when I graph it in Desmos. If I have y squared equals x, oh, hello, didn't like my 2 equals x, there we go. That is what it looks like. It's a parabola on its side, right? All I've done is I've taken y equals x squared here and switched the x and the y, right? That's the thing that I did. So all of the x's become y's and the y's become x's. So everything that was facing up is now facing to the right. That's what y squared equals x looks like. Well, root x is just the left arm, or the top arm in this case, I guess. And so if you remember what y equals x squared looks like, just draw that sideways and then erase the bottom. Because it's the same thing. It's literally the same function, but only half of it. And notice that that this thing right here, y squared equals x, that's not a function, right? And so that's why when we're doing root x, we only graph 1/2 of it. And we select the positive half, right? Rather than doing, like if I did this, if I did minus root x, that would just be the bottom half, right? So we choose the positive half because we have to only choose one to make it a function, because otherwise there's two y values for one x value, and that's no good. And then the last one that's a little bit weird, 1/x. That one. Now, this one does take a little bit of getting used to. I believe we have mentioned asymptotes to this point. There are 2 asymptotes here of this function. And yes, this is all one function. It comes in 2 pieces because 0 here is not in the domain, right? I can't put 0 in for x into this. And so what we get is called the vertical asymptote, which we'll talk more about later. Do we talk about that some? When we get to logs and exponentials, we'll do that a little bit later. But y equals 0 and x equals 0 are asymptotes. And let me dot these guys up a little bit. So that, and then we'll make it like 0.5 maybe, and then something like that. That works. This guy can be that and dotted. All right. So if we zoom in a little bit, that's out. If we zoom in a little bit, you can see that my asymptotes are the axes, and that these lines, or the function 1/x, is getting really close to them, but it never reaches them. And if you think about why, it's actually not that hard to see. That's not what I meant to do. That you'll never get there. So what's happening is, as x gets bigger, which you want to think of, x gets bigger means you move to the right on the graph. So as x gets bigger, you're doing 1 over a bigger number, which gives you a smaller number, right? 1 over 2 is bigger than 1 over 10, which is bigger than 1 over 1,000. But as long as the x is positive here, you're never going to be negative, because you're just getting something small, right? 1 over a billion is small, but it's still positive, right? It's bigger than 0. Similarly, and so you can see that's what's happening here, right? It's getting closer and closer to the axis, but never reaches it. Similarly, on the other side, but just in the other direction, because here's where the x's are negative. So if the x's are negative, the same thing is happening, right? You get a negative number, but it's getting close to 0 as that negative number gets bigger, or gets more negative, I should say. Right? So you're going to get really, really close to the axis here, but never reach it in exactly the same ways you do on the other side. Now, the other asymptote is the y-axis, where both halves of the function get very close to it in a similar way, right? As we get closer to 0, 1 over whatever you're dividing by gets bigger, right? So if I do 1 over 1, I get 1 here. If I do 1 over 2, or if I do 1 over a half right here, right, I'm going to get about 2, because the reciprocal of a half is 2. If I do 1 over a third, I'm going to get, try it again. I'm going to get 3, and 1 over a fourth gives me 4. Sorry, I'm zooming all over the place here. 1 over a fourth gives me 4. And so as I get really close to 0, right, 1 over 1,000th gives me 1,000. So as I get very close to 0, this graph shoots off to infinity on the positive side and on the negative side for the exact same reason, right? If I do 1 over negative a half, I get -2. 1 over negative a third gives me -3. So everything I just said for the positives applies equally for the negatives. And that's why the graph looks like it does. You can't ever put in 0, so there's a gap here. And as x gets very close to 0 from either direction, your function goes off to positive or negative infinity, depending on which direction you're coming from. This idea turns out to be super important if you ever go to calculus. When you talk about limits, this is one of the things you'll talk about. We're not going there. That's a couple classes away yet. But it's not too hard a concept for you to understand that as x gets really close to 0, y shoots off to infinity. Or if you're coming from the bottom side, if you're coming from the negative side, as x gets really close to 0, you're shooting off to negative infinity. And you can see that in the graph. So this is another one where you might want to, like, if you forget what this looks like, you might want to plot a few points. But when you're doing 1 over x, make sure you plot a few fractions and positives and negatives, right? Don't just do integers, because it'll actually be a little hard to tell what's going on. Do like a half and a third here, and to remind yourself what this looks like. All right. So those are your basic functions to remember what their graphs look like. And yeah, I know that there's 6 of them, but you already know this one. You probably already know this one. Xcube. Let me actually go back to my to Desmos for a second. Turn everything off here. Is that the right? That's not the right one. Hang on. This Desmos? That Desmos. That's the one I was looking at. Sorry, like I said, I got too many open. And let's look at Xcubed for a second. Now, the way you want to think about this is that this is basically a parabola where you've turned the left side over. The reason that happens, now it's not exactly a parabola, but close enough, and I'll explain why in a second. Let me demonstrate with this. Let me do x to the power of a, and give a slider. Okay. Okay, so I'm increasing. This is, I'd like to go, yeah. Actually, let me do this. 0 to 20 with a step over 1. That's what I want to do. So here's x to the first. To the second? Third. Can I just arrow keys this? No. Fourth. Fifth. Sixth. Seventh. Right? So basically, as the power goes up, you just get squarer and squarer looking graphs, with the even ones looking like a parabola and the odd ones just turning over the left arm. And the reason that you get that effect is, like, let's put in like -2 into x to the third, right? If I put in -2, I'm doing -2 times -2 times -2. 2 of those negatives pair off and make a positive, and that leaves me 1 extra one. So that makes the whole thing negative. As opposed to, let's say I have x to the fourth. I'm doing -2 to the fourth. Well, now I have 4 -2s. I have 2 pairs, so I get 2 positives make a positive. So basically, when you have an even power, all the negatives cancel. When you have an odd power, you got 1 negative left over. So that means when I put in a negative number, I get out a negative number as opposed to a positive number. But that's the only change, really. Right? It's a little bit sharper, right? As you go up in power, you can see it's getting squarer and squarer and kind of making a sharper corner there. But that's the only other change. So x cubed basically looks like x squared, but it's a little bit sharper, just a little bit sharper, and it turns over the left side. And that's actually what a cubic looks like, or that's what what x cubed looks like. So if you remember this one, then hopefully you remember this one, because when you raise to a third power, you get a negative number instead of a positive. When you raise a negative number to the third power, you get a negative number out instead of a positive one, like you do here. So because you get positives here, everything goes up. Because you get negatives, when you put in negatives, the negative part goes down for the third power, and for the fifth power too, right? For the same exact reason, for the seventh power, for the same exact reason, and all the way on up. So not only do you know what x squared looks like and what x cubed looks like, but you actually basically know, like once you know those two, you pretty much know x to the fourth and fifth and sixth and seventh and eighth and ninth, etc. Right? Because they all look the same, just a little square, a little sharper turn, but pretty much the same as x cubed and x to the third. Okay. So that was one of the that's the basic idea of the 6 parent functions, right? You remember these, and that gives you a nice base to be able to graph from. Now, here's the other thing that's not really in your book, but I really want you to think about. I've made you a little Desmos thing for it, and I put a question on the homework. I should have that up somewhere. Let's see if I've got that somewhere. Which is the following: what happens when you do stuff to your functions? Like how does the graph change when you change them algebraically? So let's say I want to compare like these two functions, f of x equals x squared and g of x equals x squared plus 1. So let's look at it algebraically, and then we'll see what it looks like on the graph, and then I'm going to kind of turn you loose on the rest of it. So I'm going to make my standard chart here. X, f of x, right? So -2, -1, 0, 1, and 2. And then same thing over here, x and g of x. And we're going to think about what's going to happen before we actually calculate this to save ourselves some time. 1 and 2, or maybe we'll do 1, we'll see. So when I put in -2 into x squared, I get out 4, as we saw a second ago. If I put -2 into g, I'm going to square the -2 and get 4, and then add 1 to that and get 5. So let's think about what happened there. So I got the same thing, right? X squared and x squared, those parts are the same. The only part that's different is the +1 in the g of x. Well, that does not affect the x, right? This part is not getting affected. It's this part, which is the y, that is getting affected, right? So the thing that I get out of this is my y. So this one was 1 bigger than that one, pretty obviously. And that's going to happen every time, right? We can pretty clearly see I'm going to put -1, get 1, put -1 in here, I get 1 plus 1, right? So every time I do this, I'm going to get an extra +1 in g. So that actually lets me fill this out pretty easily, right? So I'm going to get 1, 0, 1, and 4 here. And the g is just going to have +1 on all those y's. So 5, 2, 1, 2, and 5. All right, well, that's pretty straightforward, right? I put it, if I have a +1 in the formula, I get a +1 in the y's. Let's see what that looks like. So I have made you a Desmos link. Is it this one? Is it this one? Who knows which one it is? No, it's not this one. That one? That one. All right, here it is. It's called graph shifting with sliders. And here's the idea. I can put in whatever function I want here. I have started with x squared. This is my base function. And then for each of these, the one I was just doing was this. I was adding some number outside of my function. Boop. And if I want to see what happens when I add 1, then I need to make b equal to 1. Unsurprisingly, all the y's went up 1. Right? So at 0, 0, I went to 0, 1. When x was 1, we had 1 here, right? There was that one. You get the idea. So when x was 1, y was 1, and then on g, I had this. X was 1, y is 2. Exactly like we saw. So that's the way you want to see this, is when all the y's go up by 1, the function itself just moves up. Right? When I add more, the function moves up more. If I added a negative number, the function would move down. and you can fool around with this all you would like. You can get the link and just go to Desmos. Link's on the homework, and you can go to Desmos and just fool around with this. And so, do I have that homework up? Yeah, right here. This is question 4, right? So Desmos link is that one. That's the one I was just looking at. I want you to fool around with the sliders and tell me what effect does adding a number outside of the function have. So in other words, in other words, when I'm doing f of x plus a, what happens when I change a? And then I want you to do the same thing inside. And I want you to do the same thing if I'm multiplying outside the function. Then I want you to do the same thing multiplying inside the function. I didn't italicize those. Whatever, it's fine. That's the basic idea. So it's just an explain. Like you have to go sort of discover what's happening with this, not that, with this, and describe it. And if you don't like the y squared, you can actually put whatever function you want here, and it'll work just as well, right? I can call this 1 over x if I want to. And now the same thing's going to happen, right? So if I shifting outside, right, that moves up and down, and you can see that one moving around. Or if you want to do x to the third, you can do that one. You can just delete this thing, x to the third. And by the way, you don't ever have to worry about ruining this thing. It's not saving it for me. It's just making a new instance for you. So if you like accidentally delete a bunch of stuff, you can just go to the link again, and it'll work fine. And so you can see what happens to x cubed. Oop, that is not the one I meant to do. But you can see that when I add inside the function, I move left and right instead of up and down. But try to be a little more precise about it than that. But same thing here. Oop, I'm not graphing the right thing. Sorry. There we go. Moving up and down again. Right, so all the y's go up and down by the amount of b. All right, so that's what I want you to do on the homework, is to figure that out. Figure out like how to describe what happens to all these things. And you might have to try a few different functions and fool around with it a little bit, which is what I'm hoping for, because that's actually a really good way to learn. And when I say use a graphing utility for number 5 here, you can use calculator or Desmos if you want. I would recommend Desmos. I think it's easier. But calculator works fine if you want to do that. Okay, I think that's all I wanted to say about evaluating and graphing functions. We'll do plenty more of both of those things, so you'll get lots of practice. This is really more of an introduction and sort of a basic, like get the basics down, get some good intuition going. That's really what I want you to do, is get some good intuition going. Think about the relationship between the formulas that you see in the function and what the graph looks like. Because those things are obviously related, and they're related through evaluation. And with that being said, I think I will stop the video here, and I will see you guys in the next video.